Okay. So finishing up bottom of page 1 in section 8.2. We'll do bottom of page 1 and then we'll do page 2 as well in this video. But let's run some simulations. So this one says 76% of Americans believe that the state of moral values in the U.S. is getting worse. Use StatCrunch to describe the sampling distribution, right? The shape, center, and spread of the sample proportion for samples of size 10, and then we'll do some more simulations on the next page. So let's run this simulation in StatCrunch. Okay, so we're going to run these simulations the same way we did for the sample mean, right? We're going to go to applets, and then we're going to go to sampling distributions. This time, the underlying distribution is a binary distribution, in other words, a binomial distribution, right? And we're told 76% of Americans believe the state of moral values in the U.S. is getting worse. So the probability of success, right, the proportion of Americans who believe the state of moral values is getting worse is 76%, right? So for P, we're going to put in 0.76. Okay, then hit compute. And you get this familiar looking kind of simulation that we saw in the previous section, right, in section 8.1. But we're starting with this binomial distribution. We want to simulate collecting, here in part A, we want to simulate collecting samples of size 10. So I'm going to change the sample size to 10. And so you can run through the simulation. Here it's going to collect a sample of size 10 and compute the sample proportion, right? And the sample proportion is 0.7. So if the population proportion is 0.76, then after my first sample, I got a sample proportion of 0.7. If you're following along, you might have gotten a different sample proportion. In fact, you probably did. And that's fine, right? This is just a simulation. We can run another one. It's going to collect another sample of size 10, compute the sample proportion. That sample proportion was much lower in my case. But then if you take the average of those two, right, you're ending up with an average sample proportion of 0.6. We could do this, a bunch more times. So here's another sample proportion. Another one. Another one. And another one. Oh, wait, there's more. Thought we were done. Sorry, now we're done. Okay, so at this point we've taken 7 samples of size 10. My average, so the average of my sample proportions so far is 0.67. Which is kind of close to that, not super close. We haven't taken enough samples to really see what's going to happen. I'm going to go ahead and cut to the chase and do this 1,000 times. So if I simulate collecting 1,000 samples of size 10 and computing their sample proportions, this is what I get. So at this point, I've simulated taking 1,007 samples of size 10. Notice that the mean of those sample proportions is close to 0.76, just like we thought it should be. Okay. Notice the shape of the distribution. I would not call this bell-shaped. I would probably say the shape is skewed left. In fact, if I did this 20,000 times, you definitely get a tail out here going off to the left, right? So I would say it's a skewed left distribution. But the mean of the sample proportions is definitely the population proportion, right? The standard deviation of the sample proportions, that's a little bit more difficult to see. We'll just write down this number and kind of compare and contrast when we look at the rest of the simulations. But let's write down our observations. So for a sample of size 10, right, the shape was skewed left. The center, mu sub p hat, was equal to, well, it was approximately, we'll say it's approximately 0.76, which is equal to the population proportion, right? So no surprise there. And then the spread, sigma sub p hat, the standard deviation of those sample proportions. So in my case, that came out to 0.1339. In your simulation, it's probably different than that, okay? But it should be somewhat close, right? It should be close, but it's probably a little different. Okay, so that's for a sample of size 10. Let's redo this now for a sample of size 25. Okay, so for a sample of size 25. So I don't want to lose that. I'm not going to close out that window because I want to compare all of these things. But there was our sample of size 10. Now let's run another simulation. Binary p is 0.76. So another simulation for samples of size. In part B, we want samples of size 25. Okay, so I'm going to go ahead and cut to the chase. We'll do this 20,000 times. Okay. So after collecting 20,000 samples of size 25, again, the mean of our sample proportions is pretty close to our population proportion. The standard deviation dropped, right? So in our first simulation with samples of size 10, it was larger than it is now. So our standard deviation has dropped. And then notice also, so in our first simulation, we had a skewed left distribution. Here, we're getting something that's looking a lot more symmetric. I would say, we still do have a little bit of a tail here, but you could argue maybe that this one is bell-shaped. I'm going to say that it's slightly skewed left. Okay, but it's pretty darn bell-shaped for sure. Okay, so let's write down those observations. So for the shape, I'm going to say just slightly skewed left. For the center, again, I'm going to say mu sub p hat is approximately 0.76, which equals p. For the spread, I'm going to say sigma sub p hat, in my case, was 0.0854. Okay, well, one more simulation. Let's do this again now. Now we have samples of size 60. Okay, so I'm going to try to squeeze them all in here so that we can compare and contrast them. It's hard to get them all the same size though. Okay, so one more simulation. This time we want samples of size 60. Okay, so I'm going to go ahead and simulate collecting 20,000 samples of size 60. Okay, so now if you look at this again, the mean of the sample proportions, pretty close to the population proportion. The standard deviation went down again. Oh, you can't see it very well if I do that, huh? Well, the standard deviation decreased again. Here it was before, and here it is now. But if you look at this thing, this is symmetric. This is a bell-shaped. This is a bell-shaped distribution if I've ever seen one. Okay, so definitely the shape is bell-shaped. it's a bell-shaped distribution for sure. The center, mu sub p hat, is again approximately 0.76. The spread decreased again. In my case, it was 0.0554. Okay, so putting this all together, you notice that as n gets larger, the shape goes from being skewed left to slightly skewed left to almost perfectly bell-shaped. The spread goes from large to a little smaller to a little smaller, right? So as n gets large, the standard deviation gets smaller. The center, though, in each case, the center is always the same. The center is always just the population proportion. So putting those observations together, we end up with this fact here. So for a simple random sample of size n, taken from a population of size capital N, with a population proportion p, the mean of the sampling distribution of p hat, mu sub p hat, the average of the sample proportions, is the population proportion, right? Not surprising. The standard deviation of the sampling distribution of p hat, sigma sub p hat, right? The standard deviation of the sample proportions, is the square root of p times q over n. Remember, q is the probability of failure, right? So if the probability of success is p, then q is 1 minus p, right? Probability of failure is 1 minus p. But yeah, so it's the square root of p times q over n. Here, in this formula, you can see why the standard deviation gets small as n gets large. It's because n is in the denominator, and as your denominator increases, the overall number decreases, right? Kind of like how, 1/2 is a bigger number than 1/10, and 1/10 is a bigger number than 1/1000. So as n gets large, this fraction gets small. The shape of the distribution is a little difficult to nail down, right? We saw that as n got large, the shape became bell-shaped. And the question, as always, is how large exactly does n need to be? And the answer is p hat is going to be normally distributed, provided that n falls within these kind of parameters, right? So, well, more specifically, it's this one down here, right? N times p times q needs to be bigger than or equal to 10. So n times probability of success times probability of failure needs to be bigger than or equal to 10. If that condition holds, then we can say p hat is approximately normally distributed. Okay. This other condition is to test to make sure that it's checking for independence, right? And so it's something that we'll check for when we can, but in order to check this condition, we have to know the population size, and we're not always given that information. Sometimes we can kind of reason out what the population size is, but most of the time that condition very rarely fails. So we're probably not going to check it very much. I'll give you one example when we do, but otherwise we're probably not going to check it very much. But this second condition, we absolutely have to check that one to make sure that p hat is normally distributed, okay? So let's do that, right? Example 2 says, describe the sampling distribution of p hat if p is 0.76, n is 60, and capital N is 1 million. Okay, to describe the sampling distribution here, we're not going to use a simulation, okay? We're going to use this fact that we just discussed, okay? And this is how I would want you to do the homework problems as well. When they ask you to describe the sampling distribution of p hat, do it like I'm about to do it. Don't do it using a simulation, okay? When they ask you to describe the sampling distribution of p hat, they're asking you to describe the shape, center, and spread. So as far as the shape is concerned, we know that p hat is going to be approximately normal, provided that these two conditions hold. So let's check these two conditions, and if they're met, then we can conclude that p hat's normally distributed. Okay, so we're going to say, well, is it true that little n is less than or equal to 0.05 times capital N? Right? Is that true? Well, let's see. Little n is 60. Capital N is 1 million. Okay. 5% of 1 million would be, oh, we moved the decimal twice, right? Multiply it by 5. So how many zeros do we get? 1, 2, 3, 4. So that's 10 or 50,000. That condition is definitely met, right? Okay. The second condition we have to check. We have to make sure that n times p times q is bigger than or equal to 10. This condition sometimes fails, right? So we do have to check this one. Let's see. N is 60. P is 0.76. And Q is 1 minus P, right? Q is 1 minus P. So if P is 0.76, 1 minus 0.76 is 0.24, right? So Q would be 0.24. Is this bigger than or equal to 10? Well, let's see. 60 times 0.76 times 0.24 is 10.9, it's 10.944. 10.944. That is bigger than or equal to 10. So that condition also holds. So as far as the shape is concerned, we can say, okay, so this is approximately bell-shaped. Okay, so there's the shape. We also need to describe the center and the spread of the distribution, right? The center of the distribution, mu sub p hat, is the same thing as the population proportion p, which in this case we're told is 0.76. Okay, so there's the center of the distribution. The spread of the distribution, sigma sub p hat, that's the square root of p times q divided by n. Okay, so it's the square root of p times q divided by n. That's 0.76 times 0.24, right? Remember, q is 1 minus p, so 1 minus 0.76 is 0.24. And then divided by n, n was 60, right? So divided by 60. Let's punch this into our calculator. So I'm going to show you mine. Your calculators are all, likely, different than this, but anyway, so you're going to say square root of 0.76 times 0.24 divided by 60. Okay, you can punch it in just like that. However you punched it in, make sure that you can get this number, 0.055, well, let's round to 2. We'll say it's about 0.06. 0.06. Okay, 0.06. Okay. I'm not sure if I was blocking the screen when I had my calculator up there, so let me just show you again. Right, that's the number you should get. Okay. Rounding it to 2 decimal places, 0.06. Okay, so that's that. So if you run across a problem in the homework that asks you to describe the sampling distribution of p hat, this is what they're asking you to do. You don't have to run any simulations. You can just use these formulas, right, to do this. Okay? So let me start a new video, and we'll take a look at page 3 together.